So welcome back. We have already discussed about the shift and feature descriptors. Now it's time to discuss another feature descriptor, which is histogram of oriented gradients. So these HoG features were proposed in 2005 and later were improved in 2009 with the name of compressed histogram of gradients. Now these descriptors are mainly used for object recognition, and they are still used for many tasks with limited data availability. So if there is shortage of data, if there is a shortage of training examples, then it will be better to use histogram of gradients rather than employing for deep learning architecture. So still the histogram of gradients is used as a feature extraction method, and it is also used for wide range of applications having pose and appearance variations, and also with respect to the cluttered backgrounds under different illumination. Let us- So it actually, the histogram of gradients actually records the appearance and shape, which is characterized by the local distribution of intensity gradients or age directions. And I'll let you know that how it does that. We will be looking at the HoG intuition in a detailed manner. So what it does is it uh, takes a kind of a window like this, and it divides this each window in cells, and cells can be either rectangle or radial in this case, and each cell will accumulate a weighted local histogram of gradient directions over the pixels of the cell. I'll let you know that how this works in detail, so we'll discuss it. So let's discuss the HoG intuition. In this example, we have this region where the intensity is 0, this region where the intensity is 50, this region where the intensity is 25, and this region where the intensity is 100. So here you can see that if we try to enter from the black region to the white region, or if we leave from white region to the black region, and again if we enter from black region to the white region, there is a gradient. So once we find the gradient, what we will do is we will check how much the difference is, and this is again 100 minus 0, which is 100. Now the next gradient is in this direction, which is if we enter from black to the gray, and if we enter from gray to the white, and if we enter from white to the gray, and so forth. So all in this direction the gradient is actually 50. It's like 50 minus 0 is 50, and 100 minus 50 is 50. And similarly in the next case, if we enter into this region from the grayscale region, so this will be the third least gradient in this case, which is 25. So what it does is it gets the gradient, it records the gradient values in these directions, and for all the other directions like these red boxes, the gradient will be 0 because these are the homogeneous regions. So even if you move the window in this direction or in this direction, you will get a 0 gradient. Now let's see an example of this. Now let's say we have this image, and we take this area, we crop this area, and we get this image. So once we get this image, which is around 150 by 300, we resize it to 64 by 128. Now we actually divide this image into 8 by 16 grids, where each block has 8 by 8 cell. Now this 8 by 8 cell, I have not written the values here, but this is a kind of a window which moves and carries on with defining the values in this case. Now okay, let me just remove it. If you can see here, if we take this example, we have this 8 by 8. Now I will only consider the neighbors which is in the x direction and in the y direction. So let's just try to remove this, and this one, and this one. So in the x direction, if we look at it, the x direction, there is 70 minus 40, so it will be 30, and in the y direction it's 20 minus 70, so it will be 50. We only take the absolute values. Now once we take this, what we will do is we can compute the gradient magnitude. Now the gradient magnitude can be computed by computing the norm, which is the square root of the squared values of in the x direction and the y direction, which is approximately 58. So this value will be replaced by 58. Similarly, if you calculate the gradient direction, so the direction will be the tangent inverse of the x direction divided by the y direction, and it will be approximately 30 degrees. So here this will be replaced by 30 degrees. So that's how we compute the gradient magnitude and the gradient direction accordingly. Let me just remove this so it will be easier for yeah. So once we get this direction, now what you are seeing here is that we define this bins. So each of the value is assigned a bin, and we define the bin into 9 categories, like 0 to 20 is one bin, 20 to 40 is another bin, and 40 to 60 is another bin, and so on. So in this case, if you will see that if we move from this direction, let's say if we move from this direction, so we have this 20. Now 20 is here, this is this bin, and this direction has the value of 60, so we'll put 60 here. Now if we move forward, we have 40. Now at this 40, the corresponding value is 60, so again we will put 60 here. Now for this is the 30, the direction is 30 and the value is 60. Now in this case, the 30 is in between 20 to 40. So what we will do is we will like divide this into equal intervals, because this is in between the equal intervals, and we assign one value which is 30 to this bin, and one value which is 30 to this bin. So once we assign it, the next value which we will look at it is 25. Now 25 here is between 20 to 40, but remember that 25 is near to 20 and very far away from 40. So what we can do is we can divide the value with 3/4 and 1/4 to the either of the bin. So if it is 60, so 3 of the quarter means it will become 45, and 1/4 will become 15, which will be assigned here. For the sake of example, we consider that there is a value of 50 here, and there is so basically what we can get here is the feature vector. Now the feature vector will be something like, in first bin we have 50. Now in the second bin we have multiple values, so what we will do is we will add them all. So once we will add them, we will get the value of 135 in the second bin, and for the third bin we will again add these values, and once we add them we will get the value of 105, and so forth. So we get the total of 9 values basically. So if we consider it as a feature vector, it would be 9 values. If we consider it as a matrix, it would yield the size of 9 by 1, where 9 is the number of columns and 1 is the row. So basically this is how the feature vector is constructed in histogram of gradients. And if you will see here that these are the directions which are embedded in each of the cell. So this first one refers to the value of 50 here, as we have seen. The second one refers to the value. Okay, let me so second one refers to the value of 135. This one refers to the value of 105. Now note that with respect to this, we are having the greatest magnitude in this direction. So this is the direction where we are getting the maximum magnitude. So this is basically the angle at which the gradient direction is, and the gradient magnitude are these values which we have already calculated. Now one thing more, that how we do this is that we define the bin from 0 to 180 degree, and we define it in equal intervals for 9 bins. So we assign 9 bins with equal intervals between these angles. So let me just remove all this and let me show you the actual calculation. So this is the actual calculation which we already performed, and you can see it here. So it's a better writing here. Now how can we perform more operations here? So if you can see, this was our size of this cropped image, which was 150 by 300, and then we resized it to 64 by 128. Now with this we divided it into 8 by 16, and each of this cell is actually 8 by 8. Now in this case, what you have is you have 9 values in each of the cells, and then we will design a window of 2 by 2, and this 2 by 2 window will move from left to right and top to bottom. So if we have this 2 by 2 window, what we get is we get only one value from this window. So we'll get 7 values per row, and once we get 7 values per row, this is a kind of the 36 corresponds to the values in one window. So there are 4 cells in one window, and each cell have 9 values, so it uh, yields 36 values. So we get 7 values from one row, and we move from left to right and top to bottom. So if we move to bottom, at the end we get 15 values. So it's like if you move so it's like the first one is here, the second one is this which you are seeing, the third one will be this, the fourth will be this, the fourth will be this, the fifth will be this, and the sixth, and it goes on to 15th, not 16th. So this is the 16th one. So this is actually represented by this, which is 7 by 15 by 36, and it yields 3780 values. Let me just erase all of this. Now this is the calculation. So let's say if we have the value of 2 and 4, what we do is we normalize it. So once we take these four values, we have to normalize these values, and I will explain you why we want to normalize this. So if we have this value like 2 and 4, so we normalize it by taking the square root. It's kind of calculating the norm of it, so we calculate the square root of the squared values, and we get this value, which is 4.472, and then we divide these values by the obtained result, and we get 0.44 and 0.89. Now notice that if we scale, or if we double the intensity values from 2 to 4 and 4 to 8, and we take the norm of it, or if we normalize it, we almost get the same values as we did before. Now what is the advantage of this? The advantage of this is that if we like make the image more brighter, and if we make the image more darker by doubling the intensity levels or reducing the intensity levels to half, if we do not normalize it, then this patch would be different from the one which is obtained through the scaled version of the intensity levels, and this will create a problem for object recognition. So if we normalize it, it will be much more efficient, and we will yield the same values for the scaled intensity levels. Now this is how we actually calculate the feature vector for histogram of gradients. This graph also shows that we can yield different directions, which results in the histogram of the gradients, which refers us to the gradient magnitude and the direction of it. Now some of the examples of histogram of gradient are this. So if you may see here that if you move from this direction to this direction, you will get this particular response, which is that shows that the gradient magnitude is in this direction. Similarly, if you work towards the corner, so it will show that the gradient magnitude is in this direction and in this direction. Similarly, if you enter from this white region to the black region, it will show you that the gradient magnitude is in this direction, and so forth. Now remember that this corner and this corner have different responses. It's because you will see that they have a very minor difference in their shape. So there is the difference. So you can see that the histogram of gradient takes into account these minor differences as well. Now another example is this. So if we have the histogram of gradients of this, you will see that there is a minor change in each of the directions, and there are many responses which we get when we compute the histogram of gradients. We can reduce these responses by enlarging the cell size. Normally by default the cell size is 8 by 8, but we can increase the cell size to reduce the responses. We will discuss it when we will perform a demo, so it will be easier to demonstrate you the difference of the cell size rather than just explaining you by the intuition. So I'll explain you once we perform the demo. Now I've already explained you the benefits of normalization, so it makes it will be better if we normalize the intensity levels, because it makes them invariants to illumination and shadowing, and it is also useful for contrast normalization when we obtain the local responses. So what we do is we accumulate the local histogram energy over larger regions to normalize all of the cells in the block, as we did in our example. So this is some of the visualizations regarding the histogram of gradients. So in the first image, this is the average gradient over positive samples. Let's say if we have a positive sample, and this is the positive weights in each block, which are visualized here. These are the negative weights, so it's just the complement of this. Now this is a kind of a test image, and we compute the HoG descriptor from this, and these descriptors are then weighted by the positive and the negative weight. So you can see that the direction changes with respect to the positive and negative weights accordingly. Another example is this, where we visualize the histogram of gradients for this cycle, bicycle basically. So we can actually implement the histogram of gradients very easily. There are several built-in functions for this. Now one of the MATLAB implementations is shown here. So we can actually use this built-in sorry. So we can use this MATLAB's built-in function, which is extract HoG features. So what it does is it extracts the histogram of gradients features from 8 by 8 cell, and then we can visualize it through the built-in commands. Also, we can use the corners adjacent to the histogram of gradients to select the most strongest ones, and it will help us to filter out many responses and choose the most strongest corner feature responses. So let's see that how that works. Let me bring out my MATLAB window here. So here is the code. Let me run this for you. So we are reading this this image, which is the gate image, and we are extracting the histogram of gradients with respect to the cell size 8 by 8. Now see what happens. Now this is the response which we get, the histogram of gradients. You can see that there are many responses with respect to the directions, with respect to the gradient magnitudes. Now let's run this piece of code again by changing the cell size from 8 by 8 to 32 by 32. You can see that we have 34,596 responses for the feature vector. Now if we run this code again, now you can see that the responses have been reduced to this. Now this is what happens when you increase the cell size. You get minimum feature responses, but you lose the shape informational change. Now if you would have understood the previous one, you can visualize the shape with respect to these features, but now they are very difficult to visualize the shape. But it's not necessary to always use 8 by 8, or it's not necessary that if you visualize the shape it will be helpful in recognition. It depends on your application, and it depends on the accuracy which you obtain by like varying this cell size, because this is a kind of a hyperparameter for extraction of HoG features. So if you vary them, you can see that which cell size suits your application better, or which cell size achieves the better accuracy than the former one. Now if you just run this piece of code, what it does is it first detects the corners and selects the 3 strongest points. Once it selects the 3 strongest points, it extracts the HoG features from that particular region. So if this is basically the result which we obtain. So these are the 3 strongest points in the form of corners, and we can extract the HoG descriptor from these regions accordingly. Now coming back to the slide, so there is a difference between histogram of gradients and sieve, which are summarized to these 4. The HoG is actually used to describe entire images. So the HoG features are computed from entire images rather than from only the key point matchings, which is advantage of sieve. But sieve histograms are oriented towards the dominant gradient, whereas the histogram of gradients are not and not computed in the direction of the dominant gradients. Also, histogram of gradients are normalized using the neighborhood bins as we did before, but sieve does not normalize them. And we also saw in a previous demo video that when we normalize the scale of the sieve, how does it changes the key point features, and we actually reduce the feature responses. So of course we can use the scaling in the sieve descriptors, but it is not by default. It is not set by default. We have to do it. We have to perform the scale normalization by ourselves after applying the sieve descriptors. But in histogram of gradients, it is already a default setting to apply the normalization. So it can be used for multiple applications such as image stitching. So what we can do is we can first detect the feature points in both the images, and then we find the corresponding pairs. Once we find the corresponding pairs, we use those pairs to align both the images. Now, one of the works which I did during my PhD studies was on action recognition, and I gathered this result. So this is one of the comparative analysis between different features, and in action recognition studies, the spatiotemporal interest points are one of the most prominent feature extraction methods which were used. These are basically the classification methods which is support vector machine, neural networks, random forest, and adaptive boosting. We'll discuss or we'll shed some light on the supervised learning techniques later in this course, but till then I'll just leave as it is. So if we use histogram of gradients, of course it yields less results than the spatiotemporal interest points. But if we combine both of these results, you can see that there is quite a difference or quite an improvement in the accuracy of action recognition. So these were my findings, that we can achieve 76.76% of accuracy using both of these features and other boost classifier, and it can be further improved if we perform a kind of a pre-processing before extracting the features, like if we transform this grayscale image into depth map and then compute it. So you can see that we reduce many false responses. If you can see here, these are the false responses, these are the false responses, and these are the false responses. So these all false responses are reduced when we compute the histogram of gradients or the spatial temporal points on the depth map rather than the grayscale image. So these are some other examples where we compute the histogram of gradients from the depth map and the spatiotemporal points from the depth map, and it helps us. Why it helps us? Because you will see that there is a lot of information which we do not need, but if we transform it in the depth map, it is clear that where the gradient maps are localized, where the gradient maps are most are the most changing. So basically it provides us with the better localization, and it provides us with the better gradients. So you can use this as one of the examples to carry on your mini project. You can use this in your mini project, or you can use this in your final year projects. So feel free to ask if you have any problem, or if you have any if you need any assistance with respect to this. Now another thing which I wanted to show you is the histogram of gradient implementation through Python. So this is a small implementation of histogram of gradient. So what we are doing here is we are importing the histogram of gradients from skimage package in the Python. Now in this you will see that we are using the same orientations, which is 9, which we already have discussed. Now pixels per cells, we can change it to 8 by 8 first, and we use it for our calculation. So let's open the Anaconda prompt which we used in our last video. So let's go to the specified directory. Now here we have this code, so we will use Python and the file name is HoG_demo.py. So you can see the result here. This is the histogram of gradients using 8 by 8. Now let's see the histogram of gradients. This is basically the scaled version. So let's see the histogram of gradients when we use 32 by 32, the cell size of 32 by 32. So let's just change it here. So this, let's just make it 32 by 32. Save it, and then we will again apply scope. Now this is the result which we have got. Now you can see that the gradient directions are quite visible now, and we have reduced the feature responses, but we have lost the shape information to some extent, but still the shape information is visible. That's because we have rescaled the image itself. We have resized the image itself before applying the histogram of gradient features. So you can see this, we have resized the image here, and then we are visualizing the histogram of gradients from 32 by 32 cell. So I hope that you have understood the concept of histogram of gradients, and you know how to extract these features from while using MATLAB or Python or any of the programming language which you would prefer. So it's easy to calculate histogram of gradients, and it's super useful when you use it for the applications of object recognition and action recognition and so forth. So in the next week we'll cover another lecture. So till then, goodbye for now.